Hello. In response to some queries, thought I'd run through a couple of the more advanced frequency response questions. This is a level 3 frequency response question in which you're asked to wire up the circuit here in order to give this frequency response. As you can see, it starts with some number of zeros at 0 Hertz because it's going up even from very low frequency, and it carries on roughly horizontally at high frequencies. We've got a resistor, a capacitor, and an inductor to play around with. Okay, first thing to do is to work out how many zeros there are at 0 Hertz. And remember that a single zero or a single pole introduces an effect of 20 dBs per decade. So we'll look at low frequencies here, and we'll note that at 1 Hertz, the attenuation is about, say, minus 35 dB, something like that. And at 10 Hertz, it's close to minus 15 dB there. So we're going from minus 35 dB to minus 15 dB when we go from 1 Hertz to 10 Hertz. That is 1 decade. And this is 20 dBs. So we have an increase of 20 dBs per decade. That is the gradient of this graph. 20 dBs per decade is the result of 1 zero at low frequencies. So we have 1 zero at 0 Hertz. We also have a capacitor and an inductor. So we would expect to have 2 poles in the response, one due to the capacitance and one due to the inductance. We've got a flat frequency response at high frequencies, and that means that there must be an equal number of zeros and poles in the response, since at very high frequencies, when both the poles and the zeros are active, the poles are trying to push it down at 20 dBs per decade, the zeros are trying to push it up at 20 dBs per decade. If the net result is flat, then there must be an equal number of zeros and poles. We know there are 2 poles, there must be another zero there as well. So there's one more zero somewhere, and there are 2 poles. Right. We've got a 180 ohm resistor, a 680 nanofarad, and a 470 millihenry inductor. We know there is 1 zero at 0 Hertz. Now there's 2 ways you can get a 0 at 0 Hertz from a series of components like this. The first one is to put a capacitor in between the input and the output. Something like that. There might be a resistor in the way as well, doesn't really matter. The point is that at very low frequencies, the impedance of the capacitor is enormous, and at 0 Hertz, the impedance of the capacitor is infinite, so you would get nothing at 0 frequencies. The other way to do it is to put something between the input and the output, and then have an inductor going to ground. And if you've got a direct inductor going to ground, then that means that at very low frequencies, where the inductor behaves like a piece of wire, the output here is effectively connected to ground, so you get 0 output again at 0 frequencies, at DC. If both of these things were true, then we would have 2 zeros at 0 Hertz. We don't. We've only got 1 zero at 0 Hertz. So one of these things must be true, but not the other one. Now there's actually 2 circuit configurations that might give you that. One of them is this one. You have a capacitor here between the input and the output. That gives you the 0 at 0 Hertz. And then you have a resistor and an inductor in series between the output and ground. That doesn't give you a 0 at 0 Hertz, but it does give you another 0 somewhere else. The other one is this one. You take a capacitor and bypass it with a parallel resistor. So now, at 0 Hertz, there is a route through from the input to the output, so you don't get a 0 at 0 Hertz due to the capacitor, but you could add in the inductor like that, and now you would get a 0 at 0 Hertz due to that inductor. So each one of these circuits would give you a 0 at 0 Hertz, another 0, and 2 poles. Question is, which one of these two circuits gives you this frequency response? And to work out that, we have to analyse these circuits in a bit more detail. Okay, start with this one. Standard potential divider equation, frequency response, is the impedance between the output and ground, in this case R plus j omega L, divided by the impedance between this point and ground plus the impedance between the input and the output, which would be R plus j omega L plus 1 over j omega C. We want to express this as the ratio of two polynomials, so we multiply top and bottom by j omega C, and that gives us this. Second one. Potential divider equation again. This time the potential divider equation gives you j omega L divided by j omega L plus parallel combination of the resistor and the capacitor. So it's the product of the impedance of the resistor and the capacitor divided by the sum of the impedances of the resistor and the capacitor. Again, we want to put this into the form of the ratio of two polynomials. So first of all, in this term here, we'll multiply top and bottom by j omega C, and that gives me this slightly more pleasant formula, R over 1 plus j omega RC, and then multiply top and bottom by 1 plus j omega RC, and that would give me j omega L times 1 plus j omega RC divided by R plus j omega L plus j omega squared RLC, and if I take the common factor of R out of the bottom, that would give me 1 plus j omega L over R plus j omega squared LC, with the same j omega L 1 plus j omega RC on top. And we're now in a position to work out where the zeros are and what the resonant frequency and the Q factor of these two circuits is. Here, the zeros are at 0, as expected. If j omega is 0, then the numerator is equal to 0. The other 0 would have a value given by the value of j omega when this term is 0. And that would be minus R over L. In terms of the values that we have here, that would be, what, 180 divided by 470 milli, which is 383. Bear in mind that's 383 radians per second. If we take that and divide by 2 pi, it's about 61 hertz. Over here, the additional 0 is when 1 plus j omega RC is equal to 0. And that would be, these are strictly speaking negative as well. This would be the value of j omega when 1 plus j omega RC is 0, which would be when j omega is minus 1 over RC, which with the values that we have here would be 1 divided by 180 divided by 680 nanofarads, which is 8,170 radians per second, or in hertz. Just divide that by 2 pi, 1.3 kilohertz. Okay, at this point here, we could say 0 at 61 Hertz. That's about here. Is there any trace of a 0 at 61 Hertz? Answer, no, not really. Guess the only way there could be a 0 at 61 Hertz is if there was a pole at around 61 Hertz as well to cancel it out, and then another pole at around about the same value, which would give you the roll-off that you expected. 1.3 kilohertz. Is there a trace of a 0 at 1.3 kilohertz? Again, not really, no. The only way that could be true is if there was a pole at around 1.3 kilohertz as well, which was cancelling out the effect of the 0. So we can't immediately decide which of these two circuit topologies is true just based on the location of the zeros. We have to look at the poles as well. Where are the poles? Right, well, the standard form for a second order response in terms of the poles, its denominator, is to write it in the form 1 plus j omega over q omega naught plus j omega squared over omega naught squared, where omega naught is the resonant frequency and q is the Q factor. In both cases, we can see that the j omega squared term is multiplied by LC, j omega squared times LC, which means that this term here, the 1 over omega naught squared, must be equal to LC. And from that, we can work out what the resonant frequency must be. Omega is the square root of 1 over LC, which in terms of the values that we have here would be, let's see, square root of 1 divided by 470 milli divided by 680 nano, 1.8 kiloradians per second, which in terms of hertz, we take that and divide by 2 pi, about 281, let's just call it 280 hertz. That's my resonant frequency. What about the Q factor? Well, the Q factor is different. Here, the term in j omega is CR, which means that comparing this expression here with this expression here, we would have that Q omega naught is 1 over CR, just comparing this to there, which would make the Q 1 over omega naught times CR. And we can work that out immediately because we know what omega naught is. We've just worked it out, 1.8 kiloradians per second, divided by the capacitance, 680 nanofarads, divided by the resistance, 180. That would give you a, that can't be right. Sorry, 1 divided by all of that lot. Better, about 4.5. And the other circuit here, this topology, that, if you compare the term here with this term here, the coefficients of j omega in the denominator, you'll find that Q omega naught is equal to R over L. So now we have Q equal to R over omega naught times L, and putting in the values that we've got there, the Q would be 180 divided by omega naught, about 1800, divided by L, which is 470 millihenries, about 0.21. Right, which value of Q is correct? Well, if I had a Q of nearly 5, then I would expect to see some resonant peaking in the response here. I don't. That's making me think that the Q is much more likely to be this circuit here, Q of 0.21, and this topology would be the correct one. We could maybe investigate that a bit more detail and work out exactly where the poles are for this topology to see if they look reasonable. Let's have a go. What we've got here is 1 plus j omega L over R plus j omega squared LC, and we've identified this as having a resonant frequency of 1.8 kiloradians per second, which is 280 hertz, and a Q factor of 0.21. Where are the poles? Well, a couple of very useful expressions to know for second order systems. The product of the poles is equal to the square of the resonant frequency, and the sum of the poles is equal to the resonant frequency divided by the Q factor, Q. So, let's have a look here. The product of the poles is omega naught squared. In terms of hertz, if we work in hertz, we could write the poles in hertz as being f naught squared, where f is the resonant frequency in hertz, and just write p naught times p1 equals 280 squared. Over here, if we're working in hertz again, p naught plus p1 in hertz equals resonant frequency in hertz 280 divided by q. What does that make the poles? Well, we're going to end up with a quadratic equation if we solve this out, but there's no real way to get around that. Let's just quickly work that out, what that quadratic equation would be. We can substitute in for p1. P1 here equals 280 squared over p naught. Actually, let's just substitute in straight from there. That would give you p naught plus 280 squared over p naught equals 280 over q. And the q factor is 0.21 for the second of the two circuits that we looked at. So that would be 280 squared over 0.2, sorry, not 280 squared, just 280 over 0.21, which is 280 divided by 0.21, call it 1300, near enough. So multiply up by p naught and we get a quadratic equation, p naught squared minus 1300 times p naught plus 280 squared, which is 78,400 is equal to naught. Quadratic equation, solve, p naught equals 1300 plus or minus the square root of b squared, 1300 squared, minus 4 times a times c, 4 times 78400, all over 2. Right, let's work out that. That would be, running out of paper, hang on. 1300 divided by 2 is 650, plus or minus, right. This would be the square root of 1300 squared minus 4 times 78400 divided by 2, 586. Call it 590, it's near enough. So the poles would be at 650 minus 590, which is round about 60, and 650 plus 590, which is about 1.24 kilohertz. And remember that we have a 0 at 0 hertz, and we worked out we also had a 0 at 1.3 kilohertz. Right, back to have a look at this. Does this look like a system that has a 0 at 0 hertz, a pole at around 60 hertz, around here, and then a pole and a 0, both around 1.3, 1.24 kilohertz, which will be almost cancelling each other out because they're starting to operate at about the same frequency? And the answer is yes, it does. Starts at 0 hertz with going up at a gradient of 20 dBs per decade, as we'd expect from a single 0 at 0 hertz. At around 60 hertz, around about here, the pole starts to take effect, rolls it off, and it looks almost like a first order response going on like that, because this pole and this 0 are almost cancelling each other out. So that's looking good for this type of circuit topology. So say if it was this one, then I would have expected a noticeable peak here of around 5 dB or so. Can't see it. So let's give it a try. Capacitance in there, to there, and that goes to here. We have an inductance which goes from the output down to ground, and we have a resistance which is in parallel with the capacitance. Hooray, works. These things get a lot easier once A, you've had some practice, and B, you've been through the analysis of all of these topologies, and you've got a table of the frequency responses of them in front of you. Also remember those two extremely useful formulae. The product of the two poles is the square of the resonant frequency, and the sum of the two poles is the resonant frequency divided by the Q factor. And they are always true no matter what the Q factor and resonant frequency are. That's enough for this one.